The chapter objectives for today is that students should be able to discuss on polymers, its structure, properties, as well as limitations. And number 2, students should be able to learn to differentiate different types of polymers. As for the lesson objectives, at the end of the semester, students should be able to apply and explain ferrous and non-ferrous alloys microstructure, strengthening mechanism and its application, polymeric and advanced material structure and properties. So today, these will be the topics or content for today's lecture or subject. Number 1, we are going to look at on what is the polymer, types of polymer, general properties of the polymer, the limitations, what is the degree of polymerization or DP. Number 6, the polymer structure as well as process to produce polymer. So what is a polymer? Moving to chapter or topic number 1. Well, a polymer, any of a class of natural or synthetic substances composed of very large molecules called macromolecules. There are multiples of simpler chemical units called monomers. Polymers make up many of the materials in living organisms, including, for example, protein, cellulose, and nucleic acid. Moreover, they constitute the basis of such materials such as diamond, quartz, and feldspar, and such man-made materials like concrete, glass, paper, plastic, as well as rubbers. The word polymer itself designated an unspecified number of monomer units. Like if you can see here, monomer is actually represent many, meaning the terms for many, whereas mer is for repeated unit. And if you refer to this figure over here, for example, polyethylene. Polyethylene consists of C2H4, and if you notice that there's a repetition unit in between them, so that is called polymer. When the unit of monomer is very large, the compound is sometimes called a high polymer. Polymers are non-restricted to monomers of the same chemical composition or molecular weight and structure. Some natural polymers are composed of one kind of monomer. Most natural and synthetic polymers, however, are made up of 2 or more different types of monomer, and such monomers is known as a copolymer or terpolymers. Later on, we will see what is copolymers and terpolymers. Polymers actually can be categorized into 2. Normally, in general, they can be categorized into 2, which are plastics and rubbers. However, in engineering materials, we split it into 3, which are thermoplastic, thermosetting, and elastomer. For thermoplastic and thermosetting, it is being categorized under plastic, whereas for elastomer, it is actually referring to the rubber. Plastics are actually a wide range of synthetic or semi-synthetic materials that use polymers as a main ingredient. Their plasticity makes it possible for plastic to be molded, extruded, or pressed into solid objects of various shapes. This adaptability, plus a wide range of other properties like being lightweight, durable, flexible, and inexpensive to produce, has led to its widespread use. Plastic can be classified as either a thermoplastic or thermosetting. Firstly, let's look at what is thermoplastic or thermoplastic polymers. You see, the response of a polymer to mechanical forces at elevated temperatures is related to its dominant molecular structure. In fact, one classification scheme for these materials is according to behavior with rising temperature. Thermoplastics and thermosets are 2 subdivisions. Thermoplastics soften when heated and harden when cool. While these processes are totally reversible and they may be repeatable. On a molecule level, as the temperature is raised, secondary bonding forces are diminished so that the relative movement of adjacent chains is facilitated when a stress is applied. Irreversible degradation results when a molten thermoplastic polymer is raised to a high temperature. In addition, thermoplastics are relatively soft. Most linear polymers and those having some branch structures with flexible chains are thermoplastic as well. These plastics are normally fabricated by simultaneous application of heat and pressure. Examples of common thermoplastic for polymers is illustrated or listed in this slide over here, or in scientific way, the terms is called like polyethylene, polystyrene, polyvinyl, or polyvinyl chloride, and so on and so forth. Whereas thermosetting polymers are network polymers. They become permanently hard during their formation and do not often soften. Upon heating. Network polymers have covalent cross-links between adjacent molecular chains. During heat treatment, these bonds anchor the chains together to resist the vibrational and rotational change motions at high temperature, and thus the materials do not soften when heated. Cross-linking is normally extensive in that 10 to 50% of the chain repeat units are cross-linked. Only heating to excessive temperatures will cause severance of these cross-link bonds and polymer degradation. Thermopolymers are generally harder and stronger than thermoplastic and have better dimensional stability. Most of cross-linked and network polymers, which include vulcanized rubbers, epoxies, phenolics, and some polyester resins, they are all thermosetting. And move on to the third type of polymer, which is rubber. Well, elastomers are polymers that are having a viscosity as well as elasticity, and therefore they are known as viscoelasticity. The molecules of elastomer held together by weak intermolecular forces. Generally, they exhibit low Young modulus and high yield strength or high failure strain. They inherit the unique property of regaining original shape and size after being stretched to a great extent. Among polymer type used in the market mostly goes to thermoplastic. If you look at to this polymer tree over here, and only 10% of it use thermoset. And if you want to look at the difference of polymers mechanical properties, well, you can refer to this table here. There are reasons why polymers are important. Well, you see, both natural and synthetic polymers are remarkably involved in comfort and facilitation of human life and are responsible for life itself, for medication, nutrition, communication, transportation, irrigation, container, clothing, recording history, buildings, highways, and so on and so forth. Major industrial polymers, chemical compounds used in the manufacture of synthetic industrial materials, in the commercial production of plastics, elastomers, man-made fibers, adhesive, and surface coatings. A tremendous variety of polymers are used. Some of the useful properties of various engineering polymers include such as follows, like low density relative to metals and ceramic, good strength to high weight ratio for certain polymers, high corrosion resistant, low electrical and thermal conductivity, color transparency, processing, as well as low cost. Meanwhile, the elastomer or the plastic itself, the polymer itself has its own limitation aside from advantages just now. The limitations include low strength relative to metals and ceramic, low modulus of elasticity, surface temperatures are limited to only a few hundred degrees, viscoelastic properties which can be distinct limitation in load-bearing applications. Some polymers degrade when being subjected to sunlight and other forms of radiations or heat as well. Now, let's look at the degree of polymerization, or known as DP. But before that, we need to know the molecular weight. The molecular weight, or MW, of a polymer is the sum of the molecular weights for the moles in the polymer, in the molecules. MW equals to, actually it represents with n times the molecular weight of each repeating unit, and since n varies for different molecules in a batch, the molecular weight must be interpreted as an average. We will see the example on how to calculate the molecular weight afterwards. But before that, these are the typical values of dP and molecular weight for selected polymers. And since molecules in a given batch of polymerized materials materials vary in length, for batch is an average, it is a statically distribution is normal. The mean value of n is called dP for the batch. dP affects properties of the polymer. Higher dP increase mechanical strength, but increase viscosity in the fluid state, which makes processing more difficult. Now let's look at the example on how to calculate dP. Let's read this question together. A high molecular weight polyethylene has an average molecular weight of 410,000 gram per mole. What is its average degree of polymerization? To assess or to calculate the degree of polymerization, or dP, the formula is such as follows, whereby equals to molecular weight of polymer divided by molecular weight of mer itself. So molecular weight of the polymer is given by 410,000 gram per mole divided by 28 gram per mole per mole. If this value actually coming from its own bonding for polyethylene, we know that there's 4 hydrogens there, 4 hydrogens and 2 carbons. So multiply hydrogen atoms, multiply with 1 gram per atoms, and plus with 2 carbons times with 12 gram per mole, and equals to 28 gram per mole, and therefore divided molecular weight of polymer divided with molecular weight of mer, and you should be able to get 14643 mers. Meanwhile, if a type of polyethylene has an average degree of have an average dP of 10,000, what is its average molecular weight? So we know its formula just now. Then if you want to get the value of MW average over here, then just multiply with 10,000 of mers, then you should be able to get the molecular weight, which is equals to 280,000 gram per mole. Okay. Other than that, let's look at on polymer structure chain. You see, polymer also have different types of chain. For example, linear structure. So this is a linear. If you look at figure A over here, this is a linear chain. and all commonly found in thermoplastic. Branch structure, B, this one is branch structure, also can be found in thermoplastic polymers. Cross-link structure, this one is cross-link and normally being found in thermoset or in elastomer. Network structure, this one is network, normally being found in thermoset. So that's why if you remember just now, I did mention that thermoset cannot be heated. It will soften even though you heat it as you heat thermoplastic materials. Again, let's look at a clear review for linear structure for thermoplastic polymer. This one is branch structure, also can be found in thermoplastic polymer. Cross-link can be found in elastomer or in a thermoset. Same goes to network structure. This one can be found in thermoset. And another part in polymer are copolymers and terpolymers, like the one that I've mentioned to you in the earlier lecture. Copolymer is actually a polymer which has two types of mer in the same molecule. For example, styrene butadiene, which is used widely for automobile tires. And meanwhile, for terpolymers, it contains three types of mers like ABS, which is normally used for helmets, telephone, and refrigerator liners. You see, polymers also have its own crystal structure, and both polymers and crystalline structures are possible in polymers, not necessarily in metal only, but polymers can also have both types of crystallinity. And however, not all polymers can form crystal. For those that can, the degree of crystallinity is always less than 100%. And this one, these are the structure that you may found in polymers. Yeah, the combination of amorphous and also crystalline region. So same goes to this one. So as crystallinity is increased in a polymer, the density increases, stiffness, strength, and toughness increases, heat resistance increases, and if the polymer is transparent in the amorphous state, it becomes opaque or partially crystallized. So, okay, last but not least for today's topic, is that we are going to look at on how to process the polymers. Well, there are several types of processing involved in producing polymers like extrusion, injection, blow molding, thermoforming, as well as recycle. I think the most common that you may find is a recycle, because it is very easy to use as compared to other types of process. If you look at this pie chart over here, we can see that most of the polymers being processed through extrusion, because it shows that 36% of the pie chart, the highest percentage for extrusion showing here, followed by injection, and so on and so forth. The rest you may read it on your own for other types of processes involved. The first one is extrusion. So I'm going to show you a video on what is extrusion process. So bear with me a little while. Yep.
Plastic extrusion. This video shows how plastic parts are made by extrusion process. A typical plastic extrusion machine has hopper, hydraulic drive, heating chamber. For extrusion, the resin powders are loaded into the heating chamber through the hopper. In heating chamber, the resin powders are heated to molten state. die, and mandrel. Then the molten resin is forced into the die opening by this molten resin extruded through the die opening to a continuous length.
Okay, so that is plastic extrusion. Now I'm going to show you the process for injection, plastic injection. Well, basically, I'm going to show you all the processes involved in producing polymers. After that, we're going to look at these slides again, yeah? So this is plastic injection.
Plastic injection molding is the most common method for mass manufacturing of plastic products. The principle is simple. Inject the melted plastic material to a mold cavity, let it cool, and then solidify it into the same shape as the contour of the cavity. The process involves three main parts: injection machine, plastic injection mold, and plastic pellets. Plastic pellets in the hopper are filled into the barrel. Then, the screw transports the pellets forward. The heat bands wrapping around the barrel warm up the plastic pellets. As the pellets are moved forward by a rotating screw, they gradually melt. Once enough melted plastic is in front of the screw injects the melted plastic into the mold cavity. The mold temperature is controlled by the temperature controller. It is much lower than barrel temperature, so the molten plastic solidifies in less than a minute. The clamping plate moves backward. The mold opens. The push bar of the injection machine pushes the ejector plate and the part is ejected. After that, the mold closes and the process repeats.
Okay, that would be for plastic injection. Now let's move on to third type of process, which is blow molding. Okay, now number 4 is thermoforming.
Here is the simplest of the thermoforming methods. The plastic sheet is heated in a clamp frame until it's rubbery. A vacuum removes the air from under the sheet, and atmospheric air pressure stretches the sheet into the mold. Some regions stretch more than others, and this causes uneven sheet thickness. In this part, made in a female mold, the thickest plastic is at the top flange, where the sheet first touches the mold surface and begins cooling. The sheet becomes thinner as it was stretched to the bottom of the cavity. The distribution of the sheet in this female mold is thickest at the top flange, thinning down along the walls, and the thinnest at the base of the molded part. If we form the part on a male mold, the mold moves up to the heated sheet. The plastic first touches the metal at the projection, and this plastic is held there and begins cooling. The rest of the sheet thins as it is stretched to the flanged region. The sheet is sealed around the mold and vacuum is applied. Atmospheric pressure presses the sheet onto the mold. The sheet distribution is the opposite of the previous mold, thick at the base of the formed part and a decreasing sidewall thickness towards the flange. The flange itself will have varying thickness, thin at the corners, thicker towards the clamp frame. The uneven thickness variation from both of these molds would usually be unsatisfactory. Methods to reduce plastic thickness variations will be described later.
Okay, so that will be the 4 processes that I've shown you to produce polymer. And now let's go back to our slide. So the rest of the slides actually summarizing the processes involved to produce polymer. You see, if you notice just now, the process for extrusion and injection molding is more or less the same. Yeah, and in fact, we may use the same machine, more or less the same types of machine, but the difference is only the mold and the die. For extrusion, normally we are producing a hollow and long shape, whereby we don't use mold but we use die at the end of this at the end of the injection part there. Meanwhile, for the injection molding, it has mold, whereby we need to inject the molten plastic into the mold and then cool it down. After that, the material is being injected after it is being cooled down. So that will be the only difference between extrusion and injection molding. Whereby for blow molding is actually producing a parison. We call it this one as a parison, which being produced from extrusion molding. So at the end, I mean, once this parison being produced, then molds at both sides will fit that parison, and then after that it will blow. This side we will introduce air into it, and it will blow the parison following, and then the parison will follow the shape of the mold and producing, for example, water bottles. Okay, this one is a thermoforming, like the one that you have seen in the video just now. And last but not least is recycling. While recycle is very popular because it is the easiest way to process polymers. And this recycling process actually a stable it has stable supply of materials, because we keep using plastic, and the factory keep producing a lot of plastics to be used in the markets nowadays. Plus the recycling also economical, proven, and it is considered as environmentally friendly process of polymers. And however, the challenge is like it has additives which is sometimes hazardous to human, and then impurities in supply like labels, glass, dirt, and so on and so forth. It needs thousands of blends. So the process is like it need to have a huge numbers of plastic. You cannot produce only one plastic to be blended. And I think these would be the types of polymers that you can find in the market, whereby it is being produced through recycling or through recycle process, like PET, whereby you can find from beverage containers and so on and so forth, like then HDPE, PVC, LDPE, PP, PS, and so on and so forth. So these are the types of polymers which being produced through recycle. So that will be all for today's topic, which is chapter 7, chapter polymers. I do hope that you do understand what being delivered to you. And okay, if you notice just now for process, you don't have to go into detail for such processes or each types of processes, because later on you are going to learn on that part in manufacturing process subject. So for these subjects, you need to know on how to produce that materials or polymer itself. So with that, thank you very much for your kind attention. If you do not understand, please do not hesitate to contact me in a group or in Google Classroom. So thank you very much. See you again in the next lecture, and bye bye.